So arc measures, arcs. We did a little bit of vocabulary first. So first of all, circle, yes. An arc is just a piece of the circle. That's what an arc is, right? So when you go from the center of the circle and you make two radii, that little piece of the circle is called an arc. And it's captured by this these two radii. When you have this situation where it's the center of the circle and two radii, this is called a central angle. It's central because it comes from the center. The vertex is the center. Central angle. All right. A minor arc. A minor arc is an arc. So it's going to be captured by two segments of the circle here. And its measure is less than 180. We'll talk a little bit what it means to have a measure. But we can measure arcs the same way we measure angles using degrees. And if your arc is less than 180 degrees, it's minor. Now a major arc is part of a circle, an arc, but it's big. Now how many degrees go all the way around a circle? How many? 360. So how much would half a circle be? 180. So if you are a major arc and you pass that half circle mark, so let's say I have another radius here. So if I go all, well, I'll call it a better beat. So if I go all the way around from A, oh, look at me tracing this thing. That's not bad, not bad. Okay, all the way here. That is an arc, but it's called a major arc because it measures more than 180 degrees. It's more than half a circle. And I guess you could go all the way around, but if we pass it, we just a major arc. 180 degrees. A semicircle, what's a semicircle? Half a circle, right? It's going to measure what? 180. So if we had a diameter, right? So if this is a diameter, then this piece here would be a semicircle, and what's its measure? 180 degrees. So we're really taking fractions of the 360 when we section off these little arcs. Okay, some facts, silly. Okay, minor arcs are named by their endpoint. So for example, arc AB. So if I have a circle, I have a picture of this thing. Okay, so if this is A and this is B, I call that arc AB. Just as an aside, getting these little things really hard using a typewriter. Really, really hard. I want you to be impressed. Who's impressed that I figured out how to make this little arc? Thank you, 3 people. Thank you. Okay. Major arcs are semicircle, and semicircles are named by kind of 3 points. Because here's the problem. When I have an arc here, I've got 2 arcs. I've got this arc, and I've also got this arc. So if I call them both AB, how do I know which one you mean? Right? So what we do is we name another point, and I'll call it G, because that's what we did in the example there. And I'll call this ADB. That means go all the way around. If I only have 2 little things, go the minor arc. If I have 3 things, go the major arc. Does that make any sense? Right? You have to know which way you go around. The way we say I want the measure of the arc, this is like having an angle versus a measure of an angle. Well, this is an arc. What's the measure of AB? You can just put a little m in front, just like you do with angles. So the measure of AB, this is the actual arc itself. This is its measure in degrees. The degree measure of an arc, this is important. Very important. Not that it's all not important, but this is really important. The degree measure of an arc is the measure of its central angle. So if you open up this arc, or this angle here, you open it up 50 degrees, then we say the arc that it created is also 50 degrees. Yes? 50 degrees, 50 degrees. Oh yeah, this is a good point too. What would be the measure of ADB? If I know this AD, the measure of the minor arc is 50, how do I find the measure of the major arc? Yeah? How do I do that, Emily?
You subtract the minor measure from 360.
Exactly, right? The whole thing's 360, which is take out that word, no? And it's 310. Right? So you can get all different kinds of measures based on different things. Okay, the measure of an an arc formed by two adjacent arcs is the sum of the measure of the two arcs. This is very similar, right? We had the segment addition postulate, the angle addition postulate. I guess we can call this the arc addition postulate. It's really the same idea. This piece plus this piece equals that piece. Yeah, makes sense? I hope so. If we get segment addition and angle addition, this is the same kind of idea. So if you have another piece here, let's say I had a little loop going here, and let's say, not drawn to scale, people. Let's say that one was 30. What is the measure of BE, arc BE? 80, right? So that means. So far, not so bad. Okay. Congruence. How do you know if circles are congruent? Congruent circles have the same radius in them. And think about that. Makes sense. I think it does, right? That you're going around the same amount, your circumferences will be the same. Arcs are congruent. Okay, so if I make an arc. If they have the same measure, so you've opened up the same angle, so let's say I open this up 30 degrees, as long as I open that one up 30 degrees, okay, so far my arcs are congruent. However, the radii, they must also be congruent. So are these arcs congruent? So let's see, I've got two circles here, and we're talking about the red pieces. They both open up 145 degrees, so that's one thing to look at. And are their radii congruent? Yes. So therefore, the arcs are congruent because both the angles and the radii are congruent in those circles. Let's look at this guy here. So are these red pieces, these red arcs, are they congruent? So let's see, they both open up to 120, but the radii are not. So when I'm asking are arcs congruent, I'm kind of looking at a different thing. I'm not looking at their measure, because the measure of MN is what? What's the measure of PQ? 120. Yet the arcs are not congruent. So there's kind of two ideas. There's its measure in degrees and its actual length. If you were like, if this was made out of string and you cut here and you cut here, how long is this? And if this was made out of string and you cut here and you cut here, how long is this? Would they be the same length? No. So, well, they're what? That's a good question. Are all circles similar? That's kind of an interesting thought. She says they're similar circles. What do you think? Yeah, I think, yeah, I haven't really thought about it that way. That's an interesting thought. However, are these pieces of string here that I made in a circle, are they no? Okay. Find the measures of each arc and circle piece. So let's see. All I'm giving is a circle piece named by its center, RS. What's the measure of this arc? The measure of RS, what is it? What is it, Rachel? 110. It has a central angle, so this is going to be 110 also. How about RTS? Now this is telling me a major arc. So I'm not going to go around this way, I'm going to go around the other way. RTS. How am I going to find that measure? How do I find it? People are writing, what are we writing? How do I find it? Exactly. 360 minus 110, what do we get? Let's say 250. Degrees, don't forget your degrees. You need to put those in there. What else we got here? RST, where's that? RST. Well, what's that? What's that going to be? 180, because this is a semicircle, right? Minor arc, major arc, and a semicircle. What about ST? What's that going to be? Yeah. 70, because the whole thing's 180. You take out one, right? So we've done a lot of this very similar idea. We worked with angles this way, we used segment length. So now we're working with these arc lengths. What else we got? Oh, some new tries. All right, so try the ones kind of in the middle-ish of the page there. It's numbers 1 and 2 and 3 as well. So finish page 1, and we'll discuss. Ask questions if you need to. Let me put up what I got here. How'd we do? How'd I do? Very possible I have mistakes in this. Questions on question 1 and question 2. questions? Alright, let's see how we did. Which one? Which one? Over here? BDC, let's see. BDC, right? So I'm going around this way. So there's a chunk of 50 degrees missing from my 360 degree circle. So 360 minus 50 is 310, right? Questions? Comments? You still there? Okay, you're still there. All right, let's look at this one. Let's see. Here's what I said. Yes, ma'am. Why is the last one yes? Okay. Well, why? How come? Right. So, yes. See? So first of all, the measures are the same, right? So this measure means that this one is 135. This measure is 135. So that part's okay. So measures are congruent. That's my first thing. And now I have to look at my radii. Are they congruent circles? So because this one is the same as that one, right? Radii are congruent, but it's the radius of that circle, so they're all congruent. So the radii are congruent. So a tricky one. Other ones? You have questions on any of those? It's too easy. Too easy. Great. Let's turn it over. You get nervous. Okay. Chords. Chords are the thing you play on a guitar or a piano. That's true, but these are circle chords. So a chord is a segment with two endpoints on a circle, and you get two arcs. If you draw a chord, you got an arc here, you got an arc here. A chord that goes through the center of a circle is a very special chord. That's called a diameter, but it's a chord. And you also get two halves, but now you've got semicircles. So if you have a diameter, you're going to have 180 degree arcs. So here come the theorems. You ready? All right. In the same or congruent circles, two minor arcs are congruent. Okay, so these arcs are minor. They're congruent if and only if their corresponding chords are congruent. All right, so let's see. These arcs will be congruent if the chords are congruent, but this is an if and only if, biconditional. I can go the other way. If you have two chords like this that are congruent, two arcs that are congruent, then the chords will be congruent. Let's see. Here we go. Another one. If one chord is a perpendicular bisector of another chord, so you have two chords, they intersect. If one's a perpendicular bisector, so what does that mean? It makes a right angle, and it makes two congruent pieces. Then this first chord is a diameter. Only happens if this thing is a diameter. Just think about it. If the chord's down here, it's not going to be a bisector. It can still be perpendicular, or it can be a bisector, but maybe not perpendicular. So if you're both perpendicular and you're a bisector, you have to be a diameter. And let's see. If the diameter of a circle is perpendicular to a chord, it's kind of like the inverse of that guy, converse rather. If the diameter of a circle, there it is perpendicular to a chord, then the diameter bisects the chord. It's almost in converse, but not quite. So it's the diameter is perpendicular to some chord. I'll draw another chord. If this is perpendicular, then I know it's a bisector. If it's not perpendicular, then it's not a bisector. So 3 fun theorems. More theorems, yay! By the way, there's a lot of circle theorems, just let you know. There's a lot. So if you practice them, they get into memory better. All right, in the same circle or congruent circles, two chords are congruent, again, biconditional. If and only if they are equally distant from the center, right? Same distance. So let's see what we got here. You have two chords. They will be congruent if, now distance is measured using perpendiculars, right? Distance is measured using a perpendicular. Want to know how far this point is from this segment? You drop a perpendicular. Want to know how far this is from there? You drop a perpendicular. So these are two perpendiculars. So if this is the same distance, then these are congruent. Conversely, if these are congruent, then these distances will be the same. Yes, sir?
This theorem illustrates the first one about the minor circles.
Yeah? How does it do that?
It says, chords are congruent, these minor arcs are congruent.
Yes. So if you conclude these are congruent, you can also include the arcs. Absolutely. So we're kind of building on that. So if you have this, we could have written a theorem that said if they are equidistant, then the arcs are congruent. Absolutely. Now, we don't have that theorem. I don't know why you don't, but I mean, we could. We absolutely could, because we can prove it. Good. Yes. Excellent. All right. Let's look at a few examples on how to use this. Okay. So I got circle D. If the measure of AB is 110, now this is no different than anything else we've done. Mark your diagram. Okay, so AB is 110. What is BC going to be? What's it going to be? Why? If you have two chords that are congruent, then the arcs that they measure are congruent. So that's also going to be 110. Now these ones are separate, right? They don't build on each other. This is a whole new problem. If the measure of AC is 150 degrees, so this arc right here, I know it's this arc and not this one because it's a minor. Find the measure of this one. So what I'm going to call that X. How do I find that measure? What do you think? Okay, how can I do that? Now how do I find the ABC? You're on the right track for sure. Oh, yeah, what do you mean by half? Why am I dividing by 2? They both the same. Because these are congruent chords, if this one's X, then this one has to be X. What does it all add up to? 360. Okay, so that means that X plus X, or 2X plus 150, has to be 360. Let's subtract that 150. 0, 1, 2, 10. Okay, so X is, that's a 1, 0, 5. X is 105. So AB, 105 degrees. 150 degrees. So great, that was excellent. Well, let's look at this guy here. So I like to look at my situation. I've got a diameter, I've got a perpendicular. What do I know? What do I know? Who's congruent? I don't have a letter here. CF?
CF.
Right. So these pieces are congruent. So let's see. What are they asking? They want CD. What's it going to be? Or how do I find it? Well, is this a central angle? Oh, yeah, I know. We got to be so careful. Central angles, that would be true. If it was reaching from like there, I would agree. Yes. Why is 9x equal to 80 minus x? Okay, so what am I getting? 10x equals 8. So x equals 8. So now I can plug that in, right? Because they want me to find CD. So what's 9 times 8? 72 degrees. So this one is 72 degrees. This one's 72 degrees. What's this one? 72 degrees. Hope it works. What's 80 minus 8? 72 degrees. Good. All right, DE. So DE is also going to be 72 degrees. Now what about CE, the whole thing? So that, right, we just add them together. I guess we could call it the artificial postulate. Okay. All right, this guy. Find the measure of CU. So again, let's see what we got here. Got a distance here. This one's 16 and this one's 16. Since these arcs are congruent, what can I conclude? Those must be congruent because of the congruent arcs. They must have the same distance. So that means that those two pieces are equal. So I set them equal. Looks like 3x equals 9. So x equals 3. Now what's it asking for? CU. 2 times 3 is 6. So that one's 6. QU because it's like it's kind of continuous. It's diameter coming through, perpendicular is going to be a bisector. So we're kind of taking all these little theorems and putting them together. What's the radius of circle C? Oh, this is a good question. Radius of circle C. So what am I kind of looking now? I'm going this way. How do I know? I know part of it's 6, and I need to find a little n. I've got a little secret here. For questions like this, remember, we've got how many radii this circle can I draw? An infinite number. I think I'll draw one like this. Right, that's a radius, right? Well, what's this one? You got that, this piece is 6. What's this piece? 8. So can I find this piece? Yeah, how do I find it? Nice little, a right triangle, even better than a triangle, it's a right triangle. So a squared plus b squared is c squared. If you're good with your triples, right, I'm going to divide these by 2. I'm seeing a 3, 4, 5 triangle. Multiply that. What is the radius? 10. How cool is that? Oh, thank you, one person who thinks it's cool. One person's like, yeah, it's not cool. Everybody else is like, oh no, this sounds like more work. Is that right? Yeah. But I don't know, this to me is the fun part. Playing with it, looking for it. I saw these little puzzles. I like drawing. Anybody likes drawing like that? I'm going to ask if anybody likes geometry. Yeah, Asa does. Thank you. Thank you. One person. All right. Yes.
I now notice why you said that sort of a great basis for other theorems.
Yeah, how come?
All the theorems are used.
Yes, there's tons and tons of theorems. And if you can draw triangles, we have tons of theorems on triangles. Like, we can find out a lot of information. Awesome. All right, let's do the U-tries. Go ahead, give them a shot. Let's see how we did. Some of us are done. If you're not done, that's okay. That's okay. But if you are done, let's see. How we do on ABCD? How did I do on ABCD? Yes, perfect. Thumb up. Anybody have questions? ABCD? No one. Okay. Let's look at these guys. How we do on unit? Thumbs up. No questions? Didn't finish it. Maybe we didn't finish it? I thought E could be slightly tricky. No? No. Okay. Slightly tricky. All right. Well, great. That means you're ready for some